So, hi everyone. Today we will read a new papers. It's more thesis, to be honest with you, and it's a big one. It's called Discrete Event Simulation in Erlang, and it has been published by Andreas Ermedahl. Don't know if we can say that like that, in 1995. And this time it was made by the Department of Computer System at Uppsala University in Sweden. So this paper is freely available. You can easily find it on Google or any kind of search engine you have. To be honest, I find it directly from the site CRX website, where you have access to the whole document, if I remember correctly. So yeah, we have 98 page, and that's the same. So the goal of this document is, at least for me, to try to create a small summary of these documents, have some answers about the usage of Erlang in event simulation, and yeah, just try to read it and find some interesting stuff in it. So anyway, let's start with the introduction. Oh, maybe not. Just before starting something, just read the abstract. So the report will show all process-oriented discrete event simulation can be performed in the programming language Erlang. A small introduction to simulation on Erlang is given. The model used for discrete event simulation in Erlang and mechanism for interaction in between simulation processes are described. The author also illustrates how an extension to distributed simulation can be made. Descriptive examples on larger applications are presented. In the last passage of the report, function calls for the simulator are given. Okay, so just a small quick view of the contents. So we have an introduction, we will read it. We have what is Erlang. So actually I don't think it's really important to have to read this part, because I just I just read it before starting to read to record this recording. And it's not really interesting, because if you are already developing in Erlang, you will not learn a lot. But after that we have the simulation part. I think I will read it. It's interesting. It's only one page. Discrete event simulation model. So there is two models, and I think I will read it as well. This one as well, it's one page, so I think I will read it. So we have the simulation, discrete event simulation models, discrete event simulation in Erlang. The event handler is quite a really big subject, and I think I will just read the first part, so the representation and the two loops. Then we have the stereo simulation, probably just read the representation. Then the processes, simulation processes, I think I will read at least the first part here. Same for the resources, because that's quite huge. Probability distribution, probably just read also just the introduction, and I would like to read at least one of the two simulation we have. And finally we have the distributed simulation. This part is also quite huge, so I don't know if I will have time to read it. Anyway, this page here, the Erlang simulation glue, is really important to me, so I will read it, and the conclusion are also kinda mandatory to read. So let's start with the introduction. This project was made as a master's thesis in computer science. The project took place at Ermedahl in Oslo in Sweden. The supervisor during the project was Robert Vichting. Erlang is a declarative language for programming concurrent system, which was developed by Joe Armstrong, Robert Vichting, Max Williams, at the Ericsson and Ermedahl Computer Science Laboratories. The assignment was to examine the possibility to make discrete event simulation in Erlang, to develop and implement a model for simulation suited for Erlang, to show that the developed models can be used in one or several applications, to examine the possibility to create a distributed simulation model. I think that all these tasks have been accomplished. The section in the report will follow the order of the task. Notice that this document is intended both to be a master thesis report and a user manual. Therefore, large program and deep simulation semantics are both given in the report, and background descriptive event simulation has mostly been implemented on top of object-oriented languages while building the discrete event package in Erlang, a language with a process-based model of concurrency. It will be easy both to parallelize and distribute the simulation. When the package is written completely in Erlang, it will be possible to run the simulation on all platforms where Erlang is supported. The idea of using Erlang in discrete event simulation can be traced back to Robert Vigging and Max William. Acknowledgements. I would like to give acknowledgement to Robert Vigging and the rest of the personnel at the Ermedahl Computer Science Laboratory. That's been real fun working with you, and so on. Okay, so this part we can move. We will go directly to the simulation part. Simulation is a process of modeling a proposed and real dynamic system and observing its behavior over time. A simulation study is often constructed in order to understand the behavior of a system or to evaluate the effect of various parameters or operating policies. The simulation can be made to predict and understand the behavior of everything from a nuclear power station, a chemical reaction, to a computer operating system. Simulation can be classified into three basic types: continuous time, discrete time, and discrete event. I have myself added a fourth competitor, analytic modeling. Continuous time simulation. Continuous time simulation arises from models described by ordinary differential or partial differential equation. The state of the system is, in contrast with discrete simulation, continuously evolving. Discrete time simulation. So discrete time simulation arises from models which can be in the form of difference equation. The state of the system may change through a countable sequence of events, each equally spaced in time. Discrete event simulation arises from models describing physical systems that change their state at variable intervals. The system evolves through a countable sequence of events, each occurring at some point in time. The intervals between events are variable, and the system can therefore not be solved with a standard difference or differential equation. Several events can occur at the same point, simultaneous events. The occurrence of event can also spawn or cancel other events. The discrete event simulation is a type of simulation I have focused on the one that is most suited for computer application. Another competitor is analytic modeling, which simply consists in providing a mathematical model of the physical system under study and solving the model equation. Okay, let's take a look at discrete event simulation. Discrete event simulation is a widely used modeling technique for studying the dynamic behavior of many real-world systems. Generally, the systems are too complex to be modeled using analytic methods. Examples of discrete event systems include queuing systems and most manufacturing methods. As previously started, a distributed event simulation models a system whose state may change only at a discrete point in time. The system is composed of objects normally called entities that have certain properties called attributes. The system state is a collection of attributes or state variables that represent the entities of the system. An event is an instantaneous occurrence in time that may alter the state of the system. An event initiates an activity, which is a length of time during which entities engage in some operation. A process is a sequence of events that may encompass several activities. Entities, attributes, event, activities, and the interrelationship between these components are defined in the model of the system. Okay, so we have lot of properties and different kind of entities and objects. Okay, so we have the arrival of the event, that's called the process. We have the start service event, service activity, and the end event services. And this is the relation between process, event, and activity. Okay, fundamental to every simulation study is a mechanism to model the passage of time. Thus, every model contains a state variable called the event time. Simulated time is advanced using two approaches: fixed set increment time advance, discrete time simulation, or next event time advance, discrete event simulation. In my simulator package, it is, as I will later show, both before and during the simulation, possible to switch between discrete time and discrete event simulation. In the fixed incremented time advance method, the clock is always updated by the same time increment. After each clock update, all events that were scheduled to occur during this interval are identified. These events are considered as if they had occurred at the end of the interval. This method is useful for a system in which events only occur at intervals of some fixed time. The next time advance is a more commonly used approach. Time is in advance from the time of the current event to the time of the next scheduled event. The simulation does keep periods of inactivity. There is a calendar of events that contains the time and type of all scheduled events, usually arranged in chronological order. The simulation program must contain an executive routine for management of the clock and the calendar, a routine responsible for sequencing events and driving the simulation forward. It is behavior and construction of this executive routine that has been the real problem when the simulation package was constructed. Okay. Now, discrete event simulation models. The different parallel and distributed algorithms for discrete event simulation that were examined are all built on the elimination of the globally shared event list used in sequential simulation. Some algorithm is required to ensure that no event E is simulated until all events that affect E have been simulated. Such algorithms are frequently classified as either conservative or optimistic algorithm. Okay, conservative algorithm. Conservative algorithm blocks the simulation of an event until it is verified that the event is safe. The simulated process is only allowed to update its internal clock when all the relevant information is available. A conservative approach to simulation in Erlang can be made using Erlang's message primitive. If a process P1 simulates an event that influences P2, P1 is said to be the predecessor of P2, and P2 would be said to be a successor of P1. By calculating in advance which processes that will be predecessor and successor of which processes, a dependence graph can be constructed. When in Erlang a process P wants to perform an event E, it must first receive messages from all the processes that runs events that are predecessors to event E. When all messages have arrived, the process P is safe to proceed with event E. When the process P is finished. With event E, it must inform all its successor using messaging that it is ready. Okay. So we have an example here. We have the process loop, event action predecessor successor, event list. Wait for message predecessor. So we are waiting for some messages, do some actions, and message ready. Event successor, process loop, event list. Okay, so the big problem is how to construct the dependence graph. This algorithm may be very complicated and time consuming. It may not always be possible to predict in advance every action and interference process may take. Optimistic algorithm. Optimistic algorithms allow events to be simulated without verifying that they are safe by frequently save the states of the participating processes. When an event is simulated incorrectly, the error is hopefully discovered and the process is restored to the state before the error occurred. The internal clock is rolled back and empty messages are sent to all processes that have been affected by the process. An optimistic approach to simulation can be made using Erlang message primitives. Every process has an internal clock which is updated by itself on the set of variables that is currently aware of. The timestamp is added to every message a process sends, which indicates the current time of the sending process. Every action a process performs, the state of the variable at the moment on every message that is sent are saved in an internal list indexed on the current timestamp. When a message arrives with a timestamp smaller than the own internal time of the process must roll back to the state it was in before the time of the timestamp. All messages that have been sent to other processes must be insent with empty messages that roll back the state of those processes. Okay, so that means every process has their own clock. They keep a kind of internal timestamp with a list of this timestamp, and if they receive some messages from other processes with different time than the ones they have directly in memory, they need to roll back to a previous state. Two big problems are present. The list of performed action and send message have a tendency to grow very fast. A mechanism for guaranteeing when a state is safe must be added. The mechanism will tell the processes when it's safe to remove old action on messages from the list. The fraction of time spent on rolling back instead of simulation forward may be very large. Some algorithm for minimizing the risk for rollback must be used. The code is a bit complex. Rollback of false receive messages. The work I studied for sequential discrete event simulation was made in Simula on called demo. The name convention is my demo simulation package follows the name in the demo package. Most of the IDs found in demos can also be found in my package. Okay, let's talk a little bit about Simula. Simula was designed in 1967 under the name Simula 67 by Ermedahl and Kristen Nugard from the University of Oslo and the Norwegian Computing Center. The name reflects continuity with the simulation language Simula 1, blah blah blah. Actually, I don't really care about that. Let's move to another one. Discrete event simulation in Erlang. After investigating the different possibilities to make discrete event simulation, I was ready to choose a simulation model for Erlang. Simulation model. The model used for discrete event simulation in Erlang is the same model normally used in sequential languages, but extended with parallelism. Instead of using simulated processes, as in Simula, A process is represented with the real Erlang process. By using Erlang's lightweight processes, several processes can execute in parallel at the same time. The processes interact and are scheduled by using Erlang's message passing mechanism instead of having a global event list that all simulation processes have access to. A special process is created whose only purpose is to schedule the simulation processes. This scheduler process will be called the event handler in the following pages. By letting the event handler be responsible for creating and scheduling processes that should participate in the simulation, it is now by investigating the state of the event handler process possible to get a compact view of the whole simulation. The state of the event handler process will therefore be called the state of the simulation. Notice that in ordinary discrete event simulation it is possible to have several events at the same time, but processes that are scheduled at the event will only be able to run one at a time. In my package, it is possible to merge all events at the same time into a single event. Depending on if several processes can be running in parallel at the same event, we will say that the simulation is running in sequential, respective parallel mode. Large time gains can be made by letting several processes execute in parallel. For example, one process can execute while another is waiting for user input. But the parallelism also introduces, as we shall see, some new problems. The major problem with the event handler process solution is that every state transformation must be handled by the event handler. This will lead to a bottleneck when all simulation processes will communicate with the event handler. I thought that this was a problem, but not an insurmountable one for several reasons. Message passing in Erlang is very fast. In a normal application, it is not probable that all processes want to talk to the event handler at the same time. By distributing the simulation, the burden for the event handler can be reduced. Two were other reasons for using a simulation concept like demos. The tools for synchronization and data collection that exist in demos are desirable in most simulation applications. This was what my supervisor Robert had in mind when he gave me the task. Semantics of the simulation. In a simulation model based on process interactions, the state of the simulation is made up of the states of all the interacting processes. A process is a set of statements describing the operation in which an entity will engage during its lifetime. All the processes P1, P2 to Pn that the simulation system consists of can be grouped together in a set called E. Each state transformation Py to Py' that occurs at an event in a process P that Pi that is included in E will also result in a state transformation E to E prime. When the state of the simulation may only change at discrete point in time, the current event time of the simulation can be introduced as a parameter that affects the state of the simulation. The simulation model can now be expressed by the two-tuple E time, where E is a set of simulation processes and time is the current event time in the simulation. Okay. By using time and the fact that each process will be active or suspended and rescheduled at the event time, when it next shall be activated, E can be divided in two sets, current and EV3. The simulation model can now be expressed by the four-tuple E current EV3 time, where current is a set of processes that are indexed on the current event time, and EV3 is a set of processes that not are indexed on the current event time, so active or not active. Finally, a set of processes R which not are scheduled by the event handler but still can change the state of the simulation, are introduced. Error processes are called resources and are useful tool for the interaction between simulation processes. Resources will be deeper explained in chapter 9. The state of simulation can now be represented by a 5 tuple. Each new event causes the simulation to change from one state to another. Each time current becomes empty, all active processes have been rescheduled or terminated. The processes that are scheduled at the next event is EV3 are activated, and if P is a set of processes in EV3 that are scheduled next at the time prime, then the time transformation is empty list EV3 airtime. Okay, when process moves to current, it will be active and starts executing. Executing process can perform action. I think I will move to another part because this is quite complex. Reschedule, creating a new process. That's the list of the states, and the tuple we will use probably in the next part of the paper. So that's the event handler. I think I will just read the introduction and maybe take a look at the representation. So the event handler is a process that is responsible for maintaining the state of the simulation. Each process that participates in the simulation must be scheduled by the event handler. The event handler schedules and communicates with processes via messages. By demanding a special message from a process, each time a process makes an action that should change the state of the simulation, the event handler can hold the correct simulation state. So let's take a look at the simulation as a representation. So the active loop, resume loop. Are all processes ready? Yes. Receive message that controls the execution of the simulation. Should next event be started? No. Yes. So if it's yes, we send a message to the active loop. See, if all processes are not ready, we are just waiting in the active loop, and if it's ready, we are just looping like that. Okay. Two loops. The event handler process can be said to consist of two large loops. Each loop is a large receive statement where the event handler can receive different messages from processes. As the mechanism for receiving messages in Erlang is selective, you can choose which message you want to receive. It is possible to separate between two kinds of messages that the event handler will receive and manage. The two different kinds of messages are messages made by an executing simulation process that may change the state of the simulation. The process tells the event handler about its state change, and the event handler sends, if necessary, a confirmation message back to the process. These are calls that only can be sent and received when there are processes executing during an event. Messages that do not have to be sent by a registered process and that may change the way that the simulation should proceed in the following events. For example, stopping the simulation, change granularity, etc. These calls can only be received between events when no process is executing. By demanding that the event handler only can change the simulation when an event is finished, it is easier to keep control of the simulation. For example, imagine that the simulation is running in parallel mode. Several processes are active at the same event. If the user resets the simulation mode to sequential, only one process active at the same event, there is no way that the event handler can force the processes to stop executing. The only solution is to wait until all active processes are ready and then change the mode from parallel to sequential. The next event is the simulation will then be executed in sequential mode. Okay, that's interesting. So we have two loops. We have messages sent by processes, and those two loops will deal with all messages. Good to know. So yeah, we have the EV3, we have the whole description of the tuple we just looked before. And next we have to steer the simulation. So when the event handler may change the way the simulation proceeds, it is said to be in the resume loop. Simulation is started with a demo start code from process or user. If no other event handler process is running on the current node, an event handler process will be started. The event handler will be registered under the name demo server. The simulation is stopped with demo stop can. Okay. Resume and suspend simulation. So that is, I think, one interesting part of this paper. The simulation can be suspended, stopped after an event by a demo suspend call. Then the user has the possibility to investigate the state of the simulation. The simulation can also be stopped at regular time intervals, at every new event, or at a certain event time. When the simulation is suspended, the only way to start executing the next event is by a demo resume call. This call will make the simulation running until the next demo suspend. Call is made for until all processes are terminated. All suspend and resume calls can be made during runtime. The simulation will by default be in suspended mode when the simulation is started. The reason for that is all initialization of processes must have a chance to be made before the execution of the first event. To understand why this is a problem, look at the example below. So we have the first code. We define a function p1, so demo start, demo new p, so I think this is a new process for the simulation. P2 with no argument, and we start after that p3, and again p2. P2 it's all the one, P3 is receive something true, and after 100 seconds, and we return true. Okay, so that's the timeout feature. Depending on if the mailbox of the can process is empty or not. XP1 call may give two different results. If the mailbox is empty, it is possible that the event handler will update the event time to the next event before the second P2 process is created. The problem arises from the fact that the first simulation process and the event handler process may be created by a process that not are participating in the simulation. Normally this will be made by a function called the shell process, but the shell process will not return an exit page reason signal when the execution of the function is ready. Instead, it will go back to handle inputs from the shell. The event handler process have no way of telling when the shell process is finished, and no more simulation processes will be created. The event handler is not able to start the first event in a simulation. Okay, so only call demo resume when you are sure. Okay. The concurrency mode decides if there should be any parallelism in the simulation. The concurrency can be in one or two different modes, parallel and sequential. Okay, I think we can move to another one. We have the granularity. Is a way to change the granularity of the simulation by letting several events not equal in time be merged together into one event. We have the tracing feature. And then we have processes. Three types of processes that are useful in a simulation can be distinguished. Simulation processes. This is the processes that are created by a demo new P call and are scheduled by the event handler. A simulation process is what normally in discrete event simulation is called an entity. Resources. This is a processes used to synchronize simulation processes and collect data from the simulation. Resources are created with a demo new _r call. Resources will be treated in the next chapter. And normal processes, this is the processes that have been created with a spawn call and not a demo new underscore p call. These processes are not part of the simulation but can still be very useful. Simulation processes. Only a simulation process can be scheduled by the events handler or be part of the simulation. A simulation process can compete with other simulation processes for resources, cooperate over stretches of time, or even interrupt one another. A simulation process can be in one of the following 5 states: active, suspended, passivated, idle, terminated. The event handler can only receive calls from simulation processes when a simulation process can only change the state of the simulation when it is executing or terminates. Each state changing action in the simulation process will result in that a message is sent to the event handler. The event handler will always receive the message from the process in the same order as they were sent. Okay. Create a process, so new underscore p. Okay, I think we can just move to something different here. Create a ferry process, so we have the ferry function, cargo, suspend a process. I think we can just switch to another part of the document. We have the attributes. One difficult problem is how to transfer information about a process to another process. Similarly, this is simple. An object consists of attributes can be accessed by object reference dot attribute name call. The cargo on an object ferry may be accessed by ferry.cargo call. In Erlang, we have processes, and instead of object, a process can normally only get information about other processes through messages. I support 2 different kinds of attribute exchanges between processes: message passings on demo attributes call. So that's interesting. So we are using, there is 2 ways to communicate with those processes. So by message passing, I think that's the classic way to do that in Erlang, but this one here, this attribute call, I don't know how it works. So because of problem above with normal message passing, one more way for processes to exchange information is present, the demo attribute call. A process P1 can set an attribute with the demo set attribute call. A process is only allowed to set its own attributes. Another process P2 can get information about the attribute by a demo get attribute call. The call returns the value of the attributes or undefined if the attribute have not been set by P1 process. This form of information exchange is not synchronized, and the process P2 cannot be sure that it gets the value of the attribute P1 wants it to have. If we return to the ferry example, the process can get the cargo values both before, during, and after a cargo loading have been made. The demo attributes call is implemented using the process dictionary and the process info call. This is a use of the process dictionary that is strongly discouraged by the writers of Erlang, but I was not able to implement it so smoothly in other way. One way to handle the process of using the process dictionary would have been an attribute server process. The simulation processes will set and get attribute by sending messages to the attribute server. This can be an acceptable solution when the number of simulation processes are small, but will be a bottleneck when the number of processes increase. So I think we can switch to another part, because using a process dictionary is not really a good way to do something. Resources. What is a resources? Resources can be divided into 2 separate sets: data collecting resources. These are devices used to collect data and statistics from simulation processes during the simulation, and synchronization resources, which are processes that are used to synchronize simulation processes during the simulation. Okay, a resource is implemented as a separate process that notice scheduled by event handler. Resources created with demo new underscore air module hard list. Okay, I think we can move on this one. So we can trust is set by event handler, module export function, wire process. Yeah, how to activate passivated processes, resource report, influences, data collecting resources, coon command, toolie command. So we have some code example. Histogram. A histogram resource is used to record the roof profile of a sequence of value. That's interesting because we have the full process used to create this application. Synchronization resources, bin resources, commands. So we can have some commands. And I think I will switch to the next one because we have too much code here and I don't have the application by itself, so I can't test it correctly, and I will not recreate this application from just this specification. Probability distribution. So we have a way to okay, this is just a page. Okay, next one, a radio traffic simulation application. When a working simulation package has been constructed, the next steps were to test it with some application. The application should be able to detect missing functionality and to compare the performance of my simulation package with others. Two different companies that are working with simulation were conducted, ERA-T and erlang-punch. Even with my Danish skill, I don't really know how to pronounce that. Foreningen. So this, it's O, like in Aarhus. It's ermedahl, maybe, because actually I did later, I don't know to pronounce that in Swedish. The result from the application made for, okay, you know what I mean, will be given in the next chapter. The ERA application will be presented in this chapter, so a segment. ERA-T is a department at Ericsson in Sweden that is working with radio traffic simulation. A working model called Simon, implemented in C++, were presented at ERA-T. A short description of Simon can be found in the papers from ERA-T. The purpose of Simon Simulator is to collect all that is common among mobile telephony system simulation in a category of classes. These classes describe basic behaviors and features of all mobile telephony systems. These classes are then used when writing an application for simulating a particular kind of system. My assignment became to implement a minor part of the Simon model in Erlang using my simulation package. Okay, the radio traffic world consists of a moving mobiles that connect to antennas over area. Each place where an antenna is placed is called a seat. The area that an antenna covers, the area where a mobile can connect to the seat, is called a cell. It reminds me one of the first jobs I was working in. It was at Alcatel-Lucent. It was the interoperability. It was an IoT platform, but it was not IoT in the IoT devices. It was for interoperability between devices, and actually we were working on this kind of stuff. So it's quite funny to read something like on that. Each frequency is divided into a number of time slices. When a mobile connects to a site, it is made on special frequency and time slice on that frequency. Many mobiles can therefore be connected to one site at the same time. A mobile moves, connects and makes measurement towards sites. To generate mobile traffic, different traffic generators may be used. By having different traffic generators that covers different area and can be overlapping each others, different traffic intensities can be achieved. A mobile has a position, an antenna, and a distance to a connected seat. This parameter decides the signal strength of the connection between a seat and a mobile. Values measured during a simulation are a signal strength. Several seats, not neighbors, can send on the same frequency. The SS value is the sum of contribution in signal strength from all sets that send on the same frequency. To complicate the picture, so this is just the value of a signal. You know, when you have a mobile phone, you need to be connected to an antenna, and because you are closer or maybe you are farther from it, the signal will be not really powerful enough to have some communication. That's the same when you have your mobile phone and you are in the countryside of I don't know, of anywhere, and you don't have enough signal. And if you stay closer to an antenna, the signal will go. We have more power to communicate with the antenna. So this is the value. Carrier over interference, so relation between the calculated signal strength value and the sum of the disturbing connection. Okay, so it's when you have other mobile, I guess, using the same frequencies. Carrier over adjacent is more between the calculated and the sum of the connection on neighbor frequency in the same time slice. And downlink, so that's quite evident. So when your mobile phone is up or down, has two different connections, one uplink on one downlink, all values may be therefore regarded in both directions. And over, when a mobile moves across the seat, cell borders the SS value towards the connected seat. Okay. When a mobile makes an handover, it would first remove the present connection and try to make a new connection to another site. If the mobile fails to make the new connection is called the handover file. The error-T model. In the error-T model, only one mobile can be active at the same time. When the mobile has moved and measurements have been made, the mobile will be rescheduled to a later time and placed at the end of the list of waiting mobiles. During each activation of a mobile, it will calculate the SS, CI, and CA values, make handovers, and so on. Okay, so that's a lot of. I just wanted to read the part on Erlang. So Erlang model uses the fact that all files about the site are static. It means that the site position value and antenna value will be constant during the whole simulation. Okay, so we have a matrix table. Each mobile is represented by two Erlang processes. One of the Oh, that's interesting. So one mobile, two processes. We have the mover processes is scheduled by the event handler and generated the moving pattern of the mobile. The other process, the mobile process, is the process that calculates the SS values. By separating a mobile in two processes, it is possible to get information from a mobile during the simulation even through it is suspended by the event handler. Each mobile will have information about all the sites in the system. This will lead to that the same information is duplicated among several mobile processes, but will remove the bottleneck with one large radio path matrix. It is not necessary to represent the mobile with two processes. To reduce the number of processes in the simulation, it is easy to transform the mover mobile process to one process. Okay, so how it's working. So we have a simulation start process. It creates an event handler, creates the RM process. So this is a resource process, I guess. Create radio resource process. So radio resource talk with their neighbors. Okay, we have the TGM process. Create mover processes. The mover processes are scheduled by the event handler process. Okay, so when this one is being modified, it will send a message to the mobile process, and the mobile process will communicate with the radio sources, and you will have probably kind of synchronization between the messages or something like that. Each frequency will be represented with a process and be called a radio resource process. A radio resource will handle all connection between mobiles on site on its corresponding frequency. Manager. There are a few processes called manager that are used to start a simulation. Create mobile. Okay. Action at an event. Several mover processes can be activated at the same time when a mover process gets activated. Action at an event. Several mover processes can be activated at the same time. Okay, I think we can conclusion. Okay, that's just that. Similar model. The distance between the different organizations are kept in separate distance process. That's interesting because they are using one process for doing one thing well and keep one state. So we have the one process, I think, for example, the distance, and another one, the, I don't know, some kind of other state. Okay, distributed simulation. When the Erlang simulation package was ready, the next task was to investigate the possibility to distribute the simulation. The idea was to extend the simulation package with distribution primitives that are built on the mechanism for distribution that are available in Erlang. Fundamental for understanding distribution is to understand the node concept. Oh, I think this is an introduction to Erlang, distributed Erlang. I think we can also move to another section of this document. Global event handler 1, 2, 3, processes, resources. Create a process on the local node. The process can be created on remote node with demo local new underscore p and call. Global calls, local calls, implementation. Problem with distribution. The extension from one node simulation to distributed simulation became very simple. So some changes on the simulation package had to be made to be sure that demo suspend and resume calls only are made when they are allowed. Test to check if the global event handler is running must be implemented. Appropriate simulation application is best suited for large process simulation where many processes are activated at the same event. It is also preferable if the simulation processes can be separated in a number process group. Okay, so we have another example here. Erlang as simulation glue. An interesting extension of Erlang's usefulness in simulation purposes is as a glue between non-parallel simulation system. An Erlang process can be assigned the task to coordinate the different simulation systems. The scheduled systems can, for example, be a couple of C++ or similar system, or a mixture of both. If the different systems are located on remote nodes, Erlang's distribution mechanism can be used to distribute the simulation. As you can see, real parallel execution can be achieved in a non-parallel simulation language with the use of Erlang. The distribution granularity and the use of Erlang depends on the specific simulation application. It is therefore important that the different systems can be scheduled in a similar manner. Conclusion. Erlang is a language that is easy to learn and program. The lightweight process concept is introduced the programmer to a new way of thinking, and the declarative programming style makes the code shorter and more error secure. By using Erlang, the programmer doesn't have to handle hard programming problems like pointers in outer space. Instead, he could concentrate on the real simulation problem. The process-oriented simulation model became a little more complicated than the comparable object-oriented simulation model. This is because the simulation state is held by a single process in Erlang instead of several objects, and that simulation processes are allowed to execute in parallel. It has been my hope to hide as much as possible of the difficulties for the programmer and instead let him concentrate on the real simulation problems. The Erlang simulation model is very suitable to large simulation with big parallelism. The simple distribution mechanism in Erlang makes the extension to distributed simulation really easy. Both conservative and optimistic simulation models can easily be implemented in Erlang. The lightweight processes and the simple message pressing primitive are very appropriate for this kind of simulation. Interesting effects are achieved by letting several simulation processes execute in parallel. It is my belief that this is more like in real life where several things can happen simultaneously. By using Erlang's error handling mechanism, it is easy to achieve an error-secure simulation. The whole simulation will not be stopped if a process terminates abnormally. The use of Erlang as simulation glue is an Discrete. So I think the paper is over. If you are curious about it, it's freely available. You can read it. It's a great example of another application of Erlang. Instead of using it directly in the telecommunication world, you can use it to create some kind of simulation. That's the goal of erlang-punch, to show you that Erlang can be used in many different kind of contexts. And you should be aware that this paper was created in 1995, so that means maybe less than 10 years after the creation of Erlang, and I think it's real proof to show you this language can be used for really interesting stuff, and not only during some weird application for telecommunication system. So anyway, again, this is freely available. You can find it easily on SiteSeek. I don't know to say that, maybe SiteSeerX, and you can just read it and take a look on how it's work. You have all the example, all the figures, and all the code there. And if you are interested by doing some simulation, don't hesitate to read it again. And have a nice day. See you for the next paper session.